And there's a lot of innovation going on. Aside from the obvious of changing compression ratio, we'll also chat about the cylinder liner, balancing characteristics, efficiency characteristics, as well as some of the testing to ensure reliability. So the initial question is, what's a compression ratio and why create a car with a variable compression ratio in the first place? Well, the compression ratio, or the ratio of the maximum cylinder volume to the minimum cylinder volume, can be used to create efficiency and power characteristics of an engine. Now, Infiniti wanted to design an engine that could match the power of a naturally aspirated 6-cylinder engine while still achieving the efficiency and torque characteristics of smaller diesel engines, all with improved emissions. So how exactly does it work? Well, the engine operates on the same basic 4 strokes as any other engine: intake, compression, power, and exhaust. That said, it can completely alter the compression ratio to target increased horsepower or increased fuel economy. There are 4 basic steps for changing the compression ratio in this engine. First, a harmonic drive, essentially an electric motor, rotates an actuator arm. Second, the actuator arm rotates a control shaft, similar in principle to a camshaft, which forces a lower linkage to move up or down based on the orientation of the cam lobe. Third, the lower link changes the angle of the multi-link, which is connected by an upper link to the piston. Finally, the upper link moves from the multi-link's rotation, which causes the piston to move up or down, changing the compression ratio. So for example, if the engine was operating in its power mode but wanted to switch to an efficiency mode, the harmonic drive as shown would rotate to the left. This would then rotate the control shaft, which would pull the lower link slightly down. This would rotate the multi-link slightly to the right, which would then force the upper link slightly upward, decreasing the space between the piston and the cylinder head, thus increasing the compression ratio. Okay, so now that we understand how it works, why would you want to switch between compression ratios? Starting with the scenario of creating maximum horsepower, a low compression ratio of just 8:1 is used. This is because the engine is turbocharged. So when you pull in significantly more air and fuel with the turbocharger, you can make significantly more power. However, the likelihood of engine knock increases. Engine knock can be destructive to an engine. However, by using lower compression ratios, you can reduce the likelihood of it occurring. So when the engine is creating its peak power of 268 horsepower or its peak torque of 287 pound-feet, it's doing so by lowering the compression ratio and maximizing boost with the turbocharger. Switching between the two extremes, from a compression ratio of 8:1 to 14:1, or vice versa, can happen in 1.2 seconds. So what about when the engine operates at peak efficiency, at a ratio of 14:1? Well, generally speaking, the higher a compression ratio used, the greater the thermal efficiency of an engine is. In other words, high compression ratios mean better fuel economy. So when the engine is operating at low loads, for example when you're idling or when you're cruising down the highway, it will switch to higher compression ratios to maximize fuel economy. Now, not only does it change the compression ratio, but it also switches from a traditional engine cycle to the Atkinson cycle by altering valve timing. The Atkinson cycle leaves the intake valve open for a short duration of the compression stroke, which means some of the air-fuel mixture is pushed out of the cylinder. What this does is effectively cause the expansion ratio, the piston moving down, to be greater than the compression ratio, the piston moving up, which allows the engine to get the maximum amount of useful work out of combustion. Now, so far I've made it seem like the engine operates in 2 distinct modes, but in reality it's fully variable and can operate at any unique compression ratio between 8:1 and 14:1. Ultimately, the engine will choose the ideal compression ratio for the situation, depending on the driver's throttle input. If the driver is not asking for power, it will adjust the compression ratio to operate as efficiently as possible for the given gas pedal position. And the innovation with this engine doesn't end with a changing compression ratio. There are a lot of unique features. For example, inline 4-cylinder engines are inherently unbalanced. That means that the engines vibrate, and so to compensate, 4-cylinder engines often use balancing shafts, which add complexity and consume power, but eliminate the vibration. The reason 4-cylinder engines are unbalanced is because of the crankshaft design, which creates a secondary force that is not balanced out based on the movement of the piston. You'll notice, however, that this engine doesn't have balancing shafts, and that's because the geometry of the crankshaft assembly does not cause the piston to create a secondary imbalance. To my knowledge, there's no other inline 4-cylinder engine out there that won't have secondary balancing issues without the use of balancing shafts. So not only can it change compression ratio, but it's beautifully smooth and balanced at any compression ratio it chooses. Another unique characteristic of this crankshaft linkage is that it nearly eliminates side forces from the piston on the cylinder walls.